Okay, so in this video, I'm going to talk about gravity and escape velocity. Escape velocity is the velocity one needs to go at in order to escape from the gravity of a particular planet when you start from the surface. Um, and first, I wanted to remind you of what we figured out in the other video about the orbital velocity. And that was that if you're orbiting in a circular orbit around some big object, then the velocity you need to go at in order to maintain a circular orbit, to not fall inwards or start to slide away, is the square root of g, which is Newton's gravitation constant, times the mass of uh, the planet that's pulling you, divided by the radius of your orbit, and that radius is the distance from the center of the planet that's pulling you. So if you go that speed, you maintain a constant circular orbit. And in this video, we're going to figure out how fast you need to go to escape, to not stay in an orbit, but to leave completely. So first, I wanted to talk a little bit more about how the force law for gravity works. Remember that the force law for Newton's gravity is F equals minus g, the mass of the big object that's pulling you, times the mass of the object that is being pulled, divided by the radius squared. And it's a minus because it's negative. And I wanted to think a little bit more about that, so I made a graph showing what that force law looks like. So I've got in here the force at a radius is equal to minus g times the mass of the big object times the mass of the smaller object times the radius squared. And the reason I've got it multiplied by 1,000 is because I wanted the radius units to be in kilometers instead of meters, because that made the graph a little bit easier to read. And I've got it set with Newton's gravitation constant of 6.67 times 10 to the minus 11. And the big mass here is the mass of the Earth, 5.98 times 10 to the 24 kilograms. And then I can change the mass of the object that's being pulled, and then I'm displaying the force on that object. So now you might recognize this number here. So I've got force at 6,374 kilometers on a 1 kilogram object is negative 9.81 newtons. Sounds familiar? That's the force on a 1 kilogram object due to Earth's gravity at the surface. And that's where the 9.81 comes from that we use in lots of other calculations for acceleration. So this graph is showing what the force would be for an object, for that 1 kilogram object at different distances from the planet. So as you get closer to the center, the force gets bigger and bigger and bigger and bigger, really big, which is kind of an approximation. This graph is showing the idealized situation where all of the mass of the Earth is gathered in at the center, which is not actually quite true. And so the graph would look a little bit different if we account for that factor. But it does show you if you're at about 6,400 kilometers from the center, the force is negative 9.8 meters per second squared. And again, the reason it's negative is because it's attractive. And then you can see that the magnitude of that force gets smaller the farther away you get from the surface, from the planet. So at 10,000 kilometers away, the force is down to negative 4 newtons instead of negative 9.81 at the surface. And if I go further away, say 20,000 kilometers, it's down to about 1 newton. So you can see that you can get really far away, and the force is still really is measurable. It's not huge anymore. It wasn't huge to begin with, but it's certainly measurable. And then I just wanted, for fun, to think about, well, what happens if you keep going farther and farther out? Let's go all the way out to 100,000 kilometers, which is about a third of the distance to the moon, and it is still a measurable 0.04 newtons. And to save time, rather than scrolling out here, I can just type in the number I want. So the distance to the moon is about 380,000 kilometers, 1, 2, 3. And the force from the Earth on a 1 kilogram object at the surface of the moon is 0.0027 newtons. So part of what I'm trying to point out here is that the force never completely goes to zero. It's not zero. I can keep adding zeros to this, and it's not zero. It becomes immeasurably small fairly quickly. But even at the surface of the moon, the force on an object is measurable. That is a definitely measurable force with the right kind of equipment. So that tells you that Newton's gravity does not ever entirely go away. So this idea of escaping to completely escape from Earth's gravity we have to think about that a little bit more. And if you think about it, it has to be that there is some force even at the moon, because the thing that is keeping the moon in its orbit around the Earth is the force due to gravity. The force due to gravity between the Earth and the moon is quite a bit bigger than this, because the moon is larger than the 1 kilogram. But that gravitational field, the influence of the Earth, extends out over a massive distance, because that r squared never completely goes away, and the mass of the Earth is really large. So it has a large influence over a very large distance. And that means that we're going to have to think carefully about what it means to really escape from Earth's gravity. So let me put that back to the 6370 at the Earth's surface. You can see the negative 9.8 meters per second squared that comes from the acceleration due to gravity at the Earth's surface. And we're going to think about what does it mean to really escape. And to do that, I'm going to go back over here and then think a little bit again about something we talked about in the previous week about roller coasters. The idea of a roller coaster is that you have a certain amount of energy in the system, and that once you set the roller coaster going, you make sure that there's always enough energy left to keep the coaster going. So you start out at the high point right here with a certain amount of potential energy. So you've got potential energy initial at that high point, which is the mass of the coaster times the strength of gravity times the height. And you've got a kinetic energy of 0 because you are not moving. If you imagine the classic roller coaster where it very slowly cranks you up to the high point of a hill, and then you crest the hill at basically 0 speed, and then you just start to fall. And you go, wah! And as you fall, what happens is at this point right here, you've got 0 potential energy. So the PE equals 0, and you do have KE. So the kinetic energy comes from turning that potential energy into kinetic, and it's equal to 1/2 the mass times the velocity squared. And then you start to climb again, and then you get to this peak, and you've got some potential energy and some kinetic. Because you didn't quite go to the same height that you went to before. The reason that typical roller coasters are designed like this, where the first hill is the highest one, is so that it's okay to have friction and other things that slow you down a little bit so that you keep making it to the next hill. But if there weren't any friction, if there weren't any outside influences other than gravity causing you to speed up as you fall down and then gravity causing you to slow down as you go up, what you would see is that the potential energy that you started with plus whatever kinetic energy that you started with, if you happen to hit that first hill with some speed, would be constant. It would never change through the entire ride. And that means that you could figure out how fast you're going to go at any moment on that track just by knowing how high you are off the ground. Because as you fall, you trade that potential energy and you turn it into kinetic. As you rise again, you trade the kinetic and turn it back into potential. And because the two things together have to add up to a constant, the same number the whole trip, you can always solve and figure out what your velocity is at that moment, knowing the height. So the potential energy is the mass times gravity times the height. The kinetic energy is 1/2 times the mass times the velocity squared. And that equals whatever the total energy was that you started from. Again, assuming no friction, and no other outside influences acting on the roller coaster. So let's use that analogy, that metaphor with the roller coaster, to think about how we can understand how to escape from Earth's gravity. So the idea is, let's imagine a roller coaster that starts at the bottom. Starts down here. And you climb and you climb and you climb and you climb. And how do you climb? You climb because you had some kinetic energy to begin with. So you've got KE initial. And you are trading that kinetic energy for potential energy as you climb, because as you get farther and farther away from the surface, as you go up that hill on the roller coaster, your potential energy goes up and your kinetic energy drops. So what I want is to imagine I've got this really, really high hill that I want to get up. And I want to figure out how to make it so that my roller coaster will start at the bottom with some initial kinetic energy, some initial velocity, and it will rocket upwards, losing its kinetic energy as it goes, gaining potential energy, and it will have just enough energy right at the start so that when it gets up to that high point, it will not fall back down again, but it'll keep going. I want it to reach the point where the potential energy is 0, with just a bare amount of kinetic energy left over so it keeps going forever after that. So that's a little funny. I want to start at the bottom with some kinetic energy. I want to climb up to the top with just enough kinetic energy so that I can escape, and the top is the place where potential energy is 0. Okay, so if the potential energy is 0 at the top, what was it at the beginning? If I climbed, I gained potential energy, and it's 0 at the top, that means it must have been negative to begin with. PE initial is negative. Why was it negative? It was negative because the force due to gravity is negative. It's attractive. It pulls you down. Also, it's negative because the force never, ever, ever becomes actually 0. If I go back to that graph again, the point I was trying to make there is that the force is not actually 0 no matter how far away you get. But if I imagine going to an infinite distance, the force approaches 0. It gets closer and closer to 0 the closer I get to an infinite distance. That's what I mean by escaping. I mean you get to an infinite distance, the point at which the force is 0. And the force is 0 when the potential energy is 0. And it was negative before that. So the idea, this is a convention that physicists have come up with as a way of bookkeeping, where all this energy comes from and where it goes, is to say, let's say the potential energy down here on the surface is negative. It's 0 when you're really, really far away. And then as you go up the hill, your potential energy is increasing because it's getting less negative, and your kinetic energy is decreasing because you're trading that kinetic energy for potential. And then you finally escape when you hit that 0 point at an infinite distance with a tiny bit of velocity left over. That is the idea, and that's the metaphor with it. So to turn that metaphor about the roller coaster into an insight that allows me to calculate how fast I actually need to go to escape from the Earth, I really want to turn this potential energy into an equation, an explicit formula that allows me to calculate exactly how fast I need to be going in order to escape. And so to do that, I'm going to make a connection between this potential energy near the Earth's surface and the force due to gravity. And that formula works no matter where you are around the Earth. This works when you're close to the surface. So the G that we're used to, that we've used a few times, is the acceleration due to gravity near the Earth, and that is 9.8 approximately meters per second squared. Where does that come from? That comes from Newton's universal gravitation law. If I take that force law and write out negative g m over r squared times the mass of the object that's being pulled, and then plug numbers in for 6.67 times 10 to the minus 11, that's Newton's gravitation constant, times the mass of the Earth, divided by the radius of the Earth squared, that's the 6,370 kilometers. That ends up being, remarkably, 9.8. That's where the negative 9.8 comes from. Negative 9.8 meters per second squared times the mass. So that's the force, that's where the 9.8 comes from. It comes from that equation, putting in the right radius and the right mass for the Earth. Okay, so that's m times g times the height right there. That means I need to multiply by the radius, or the distance from the center. So if I take this equation for Newton's force and multiply it by the radius, force equals minus g times the mass of the Earth times the mass of the object divided by the radius squared times the radius again, you get a cancellation. That r cancels one of those. That's no longer a force anymore. That's the potential energy. So writing that out in full, you get that the potential energy due to the interaction with the Earth is negative the mass of the object times gravitation constant times the mass of the Earth divided by the distance from the center of the Earth. That is the potential energy at different radii. And notice that that decreases. It gets smaller and smaller because as the r gets bigger, this thing gets smaller and smaller and smaller, and it never ever gets exactly to zero. But when the r gets close to infinity, the potential energy goes to zero. So potential energy goes to zero as r goes to infinity, which is exactly what I want. I want an equation for potential energy that starts at some negative number on the surface and becomes zero when you escape. Okay, so what I'm going to do is I'm going to take those equations for the kinetic energy and the potential energy at the surface when I rocket my ship upwards and use it to calculate how fast I need to be going to escape. So let me get myself a new page, and then I've got that the kinetic energy initial plus the potential energy initial has to be a constant, because you're not going to get any new energy as you are climbing up out of the hill or the valley to get away from the Earth. And you're not going to interact with anything else. We're going to ignore friction and air resistance and things like that. And that has to be equal to your kinetic energy plus your potential when you've escaped. So your kinetic energy final plus your potential energy final. All right, well, what's the potential energy going to be once you've escaped? It's going to be zero, because that's what the potential energy is when you've escaped to an infinite distance away from the Earth. What's the kinetic energy final going to be? It's also going to be zero. We're trying to figure out the velocity that is just barely big enough to get away. If you're going any faster than this velocity, you would still have some extra kinetic energy left over once you've escaped, and you would keep going even faster when you leave. So this is I'm calculating the minimum, and that means that the energy at the end is zero. So the total energy of the system is always zero. That's actually kind of interesting. So the constant that the total energy is equal to is zero. And then I know that the kinetic energy initial is going to be whatever my initial velocity was, 1/2 m velocity initial squared That's the thing I'm trying to find, whatever that initial velocity is to make this work. Plus my potential energy, which I just figured out was negative m times g times the mass of the Earth divided by the radius of the Earth. And you can see how that can possibly add up to 0. We've got a negative number for the potential energy, a positive number for the kinetic energy. Those two add up to 0, and those two are just enough to allow me to escape with 0 energy left over as excess. All right, so let's start rearranging this. And first we find out that the masses of the object that we're trying to escape cancel out. So the velocity you need to escape does not depend on how big the object is. The force you need to escape does depend on how big it is, but not the velocity. So then let's move some things over to the other side. I've got vi squared over 2 equals positive big G times the mass of the Earth divided by the radius of the Earth. Then I'm going to multiply the 2 over to the other side and take the square root. So the V initial that I need is equal to the square root of 2 GM over R. That's the velocity you need to escape from the Earth. We're going to throw some numbers in to figure out what that is. But I want to remind you of what we did in that other video about orbital speeds and what's on the other page right here, that the orbital velocity is root gm over r. So let me come back over here. The velocity to orbit is root g big M over r. It's very similar. It's exactly the same dependence. So this is the radius of the Earth. This is the radius of the orbit. There's big G and the mass of the Earth, big G and the mass of the Earth. The only difference really is that 2. So the velocity you need to get to escape from the planet is root 2 times bigger than the velocity you need to orbit at a particular radius. That's really interesting. It's not a whole lot bigger. So there's a certain velocity that will get you in an orbit. There's a different velocity that's about 1.4 times bigger that will allow you to escape. So let's plug some numbers in, and we'll do that for the Earth. So root 2 times 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 kilograms divided by the radius of the Earth. That's 6370 kilometers again. 6370 times 10 to the third to put it into meters. And that works out to around, rounding and not showing you the calculation, 11 kilometers per second. So that's how fast you need to go to escape, and you need to go a little less than that in order to make it to an orbit. One more observation about this is that because the mass of the planet you're escaping from is on the top of this fraction, that means the bigger the mass, the more velocity you need to begin with to escape. And also the smaller the radius. If the radius is on the bottom and it gets smaller, that means the whole velocity gets bigger. So a small radius means it is tougher to escape, and a big mass means that it's tougher to escape. If you put those two together, like in a black hole, you've got a really enormous mass and a very small radius, and those two together make it essentially impossible to escape. So it's interesting. We were able to use this analogy about the motion of a roller coaster and climbing out of a valley to get up and escape with no excess energy left over, and we get 11 kilometers per second as the escape velocity from the Earth.